Okay, now I'm recording. All right. So we just finished up working on sampling distributions. And what we were doing in sampling distributions was we were given information about some population that we were interested in, and we were drawing conclusions about it. And so we were kind of done with that. We'd finished it just kind of on the last day we were talking about it. So we're going to move into some newer stuff. I am going to mute you guys. If you have, so say goodbye.
Bye.
If you have a question while we're going through this, you can raise your hand and ask the question, but there's just ends up being a lot of reverb and stuff if I don't mute you guys. So we were looking at these sampling distributions where we knew what our population parameter was. They told us, 30% or whatever of people did stuff. The next part of this unit is on confidence intervals, and it's our first kind of step into this concept of inference, which is a huge thing. So it's kind of unfortunate that it comes at the end of the year like this, and we're not in class to talk about it. But inference is what happens more realistically. We don't generally know our population parameter. Instead, we have to take samples and try to infer what's true about our population from those samples. And so it's called inference because we don't know a population parameter. So if you guys remember when we all like drew those little chips and they had our test scores on it and we went around and took samples, we didn't actually know the actual percentage or average score on that test. We all just took samples and drew conclusions based on the samples, and that's more realistic. So I want to remind you guys what we were doing with the sampling distribution. So I'm going to turn on my document camera for just a second. Let's switch to that. Hopefully this will work. Okay, give it a second. There it is. All right, so you guys can see me write stuff. So what we did with our sampling distributions is we had a proportion that was our population parameter, so our population proportion. And we created we calculated a standard deviation for that. Do you guys remember the formula that we used to find that standard deviation? If you remember it, type it into chat. What did that formula look like? So this is what we were just doing. Oh, there we go. Now we're getting them. And so what I'm seeing from us is that, oh, someone's showing up late. That when we were finding our standard deviation, remember that we would take P, which was our population parameter, we would multiply it by Q, and we would divide it by N, and that would be our standard deviation, right? So a lot of you were telling me that, which is cool. Now I want to take a step back from that and have you guys remember our normal model and our empirical rule. Do you remember how to finish the statement that says 95% of all data is within what? %95 of all data, if I have a normal model, how much, 95% of all data is where? Right, it's within 2 standard deviations of the mean. And so if I have a model that I think is normal, then I should be able to kind of make a range of values and say 95% of my data should be within this range. So let's just pretend that we took a sample of, say, 50 high school students, and we asked them the question, do you like burritos? And I had 60%, or I know that 60% of high school students say they like burritos, right? So I have a sample size, I have a population parameter because I believe that 60% of high school students say yes, they like burritos. Can you guys calculate what the standard deviation would be for that sample? You guys are supposed to have a calculator with you. So what is the standard deviation for that sample? Good. Okay, good. Those numbers look good. So when I find the standard deviation for this, we would have done 0.6 because that's P times 0.4 because that's Q, and the sample is a size 50. So square root all that, and you guys are telling me the right number, 0.0692, and that's my standard deviation. So I should be able to say, if I think that P is right there at 0.6, that I should be able to add 2 standard deviations to that to find that range that goes up to the top. And I should be able to subtract 2 standard deviations from that to kind of find the lower bound for that. Because if this is a normal model, I should have 95% of my data within 2 standard deviations of the mean. So I've already figured these numbers out, but if I take 0.6 and I add twice of this 0.0692 to it, I get a value of 0.738. And if I subtract 2 standard deviations from it, I get a value of 0.462. So according to what I know about a normal model, that would mean that 95% of all samples would have, whoops, that's not how you spell that, would have a p hat value, remember p hat is for the sample, that's between 0.462 and 0.738. And that's just based on the model that I have. So what this means, when I know what P is and I count 2 standard deviations above and below, that out of all the samples that I took that are this size 50, 95% of them would show that their sample proportion is between 46.2% and 73.8%. Okay, does that make sense so far? Sound okay? Let me know. Give me a yes, a no. Do you have any questions so far? Okay, so we look good so far. All right, but here's the thing. I don't have a worksheet particularly for this one, Deanna. I am going to print out, I think I might have posted already that I have like some PowerPoint slides, and this recording will be posted in class, in Google Classroom as well. So hopefully that'll give you the stuff that you need. But this right here, this should be just kind of review for us, right? Because this is just working with a normal model. So this is not inference. This is just us working with the model that we have. So what we have to deal with, though, is the fact that most of the time, I don't know my population proportion. I honestly don't know what percent of high school students say they like burritos. And so I can't be that confident and say, oh, I know that the proportion is somewhere in here. So what we do instead is we take a sample. I took a sample. I asked you guys on the last test, do you like tacos or burritos? And so there was about 50 of us, n equals 50. And I could say for my sample, I'm going to call it p hat now because it's not my population parameter. Instead, it's just my sample proportion. Let's say for my sample proportion, 60% of you said that you thought, or that said, yes, you like burritos. These are now statistics. They are no longer my population parameter. But I want to take those values and I want to change them into something that helps me understand what could be true about my population. Because there is a number that's true for the population, I just don't know what it is. So I can't really calculate a standard deviation because I don't know my population parameter. So instead, in this process of inference, we're going to create something that we're going to call the standard error. And it's just something that's going to give us a range. And the way that I calculate a standard error, this is going to be a somewhat familiar looking formula, but it's p hat times q hat divided by n. It's exactly the same formula we were using for standard deviation. It's just now I'm going to base it on my sample that I took rather than a population parameter that I don't know. So if we have the same data, my standard error is going to be that same value of 0.069, right? I still know that idea of the normal model that 95% of my data is supposed to be within 2 standard deviations of the mean. So I can still go through exactly that same process and take my p hat value, and I can add, instead of adding 2 standard deviations to it, I can add 2 standard errors to it, and we just use SE to represent standard error, right? So right there. Or I can subtract 2 standard errors from it, and I get exactly the same values I had before, 4.62 as my lower boundary and 7.38 as my upper boundary. Now, I'm not expecting you guys to know how to do this right now. I'm just kind of showing you this process. And next class, we'll spend more time actually calculating this. But I want you to see I'm doing the same process that I did with my P, my population parameter, and I'm building this interval. Now, our hope when we make a confidence interval is that we are hoping the actual value of my population parameter is in this interval. So what I'm hoping is that when I take my statistic and I build out this interval around it, in this case, adding and subtracting 2 standard errors, that I have contained the actual value, that p-value that I don't know what it is, but I'm hoping it's in this range. So I can't make a statement like I did on the other page where I said 95% of the data is in this range. But because I created this data that is in this case, 2 standard errors below and 2 standard errors above, I'm still in that 95% range, right? So I still have 95%, but I'm no longer able to say 95% of the data is in this range. But instead, now I can say that I am 95% confident. That's where the confidence comes from. I am 95% confident that the true proportion, right, we don't know that, of high school students who like burritos, I'm writing this out because this is the exact wording that you want to use, is between 46.2 and 73.8%. And so because we use that idea of 2 standard deviations above and below, we can refer back to the 95%, and I can say that I am 95% confident. I can't be 100% confident because maybe I didn't catch it. Maybe it was something else and my sample's just wrong. But I can say I'm 95% confident that this interval that I made, 2 standard deviations above my sample and 2 standard deviations below, contains the number that is that true value that I'm trying to find. And that's kind of the whole idea of a confidence interval. Okay, So that was a lot that I just dumped on you right there. What kind of questions do you have right now? Is it kind of making sense? Anybody have anything they need to ask? David says he's okay. Yes, Aya, exactly. Right, it's okay if you don't get the math part, because we're going to spend more time next class actually doing the math part. I think that I posted like a worksheet for homework, and I'm not, if I think there's a calculation on it, but we don't really need to worry about. How would we identify when reading a problem that we would need to use inference? It's going to tell you in the problem, it's going to say you took a sample, and it will probably flat out say make a 95% confidence interval, which is what I just made, a 95% confidence interval. So we can alter the level of confidence by changing the number of standard errors that we multiply by. Like Aya said, if I add and subtract 3, would it be 99.7? Exactly. If I added and subtracted 1, I'd be at 68%. Now, 68% is not being very confident, right? 68%, I'm 68% sure I've captured it. 99.7% is pretty confident, but remember, if I add 3 standard deviations, that interval is going to be a lot wider. I'm going to go out another, 6 or 7%. And so I'm more confident that I've captured it, but my interval's less precise. So that's one of the things that we have to think about in terms of how we do this. How do we calculate 68, 95, 99.7? That's a good question, and we will get to that, and you will have to use normal tables. But I will tell you, there's kind of, there's some specific values that we see a lot, 90%, 95, 98, 99. And I'm going to tell you what we multiply by for those later. Okay, so defining inference. Inference is when I only have samples, I have sample statistics, and I use those to draw conclusions about what's true about the population I'm interested in. So I don't know my parameters, I don't know the actual proportion. So I take a sample and I use that sample to try and infer what's true about the population proportion. So I just want to show you one little drawing that I put into the PowerPoint slides, which I decided not to use. And it's, let me see if I can find it real quick. It's this little drawing right here. You guys all see that? If you think about creating confidence intervals, like we each took a sample. When we were doing that thing with the test scores, everybody took samples. You asked 5 people, what score did you get? And you found a mean. We each could have taken that mean and created a confidence interval. So this is an example of each of these little lines here represents a confidence interval. That dot in the center is the sample mean or the sample proportion. And those lines kind of indicate where the boundaries, the low value and the high value is for each person's interval. So every single one of us could have made a different interval because every single one of us asked 5 different people. Now that line that's running through the middle, that's the actual population value. So if you see in this, with all these intervals, most of them contain the proportion that we were looking for, the population parameter. But there are a few, this one right here, this one right here, this guy down here, that didn't contain the parameter we were looking for. And so that's why with a confidence interval, we're rarely going to say I'm 100% confident. But we want to make the interval large enough that we hope we're capturing the proportion, but not too large that our numbers mean nothing. Like it'd be really easy for me to say, I'm 100% confident that the average score was between 0 and 100, right? But that doesn't mean anything. And so we have to decide the level of confidence, which is going to affect how many standard errors, and that'll help us decide how big or small that interval is. Okay, so this is just the conceptual stuff. So we're not, I'm not expecting you guys to be able to do that math yet. We'll look at the math next time. I just want us to start to get an idea about what a confidence interval is and how it helps us to kind of get an idea of what's true of our population proportion. I'm going to post a link to a YouTube video that I found that the gal does a really good definition of what a confidence interval is. She's from Australia, so she has a cool accent. But I'll post that, so if you guys can take a listen to that before we have our next class. And like I said, I did post some questions, and they're really just kind of basic questions to see if we're starting to get an idea of what we're doing in a confidence interval. So I'm going to switch back to my camera. I think I'm going to unmute you guys for a second and see if we have anything to say. Everybody doing okay?
What is Kai babbling about over there?
I'm enjoying these breaks, is what I'm doing.
I feel like I made an error in muting you guys.
Corona.
Okay, so does the concept of it, is it okay? Are we getting the idea of where we're going with this?
Yeah.
Yeah.
Mostly.
Okay, so next time we'll get into the math part of it more. So you'll want to make sure you have a graphing calculator with you next time. I noticed online Texas Instruments has actually given free subscriptions to their like their online calculator, like the one I have on my laptop. So if you don't have a graphing calculator at home or with you, go to the Texas Instruments, the TI website, and there may be a link, and you can actually download that simulator that I use in class, so you'll have a graphing calculator of your own. As far as the homework goes, just do the best you can and then post what you have. I'm just grading it to make sure that we're kind of getting started on it. I do have office hours today, so I have an hour from 1 o'clock to 2 o'clock where if you have questions, you can just drop in and I will answer your questions. As far as reperformances and extensions go, we're forgetting the deadlines on the extensions, so don't worry about a deadline passing on that. If you're working on a reperformance, you can still turn in those reperformance practice questions, and I'm trying to figure out the best way to make that happen so we're not sitting on incompletes for the next 4 weeks or whatever. I haven't quite nailed it down as to what that testing is going to look like, but that's where we're at. So I think that's it for today. You guys okay?
Yeah.
Yeah.
I'm dying.
You're dying?
Yeah.
That happened.
Oh, I'm sorry to hear that.
Oh, wow, so funny, so hip and modern. Joe yawning.
Okay, all right, with that, I think I'm going to mute you guys. And I'm going to stop recording on this. And I will see you guys again on Tuesday morning or today during office hours if you have any questions. All right, bye guys, I'll talk to you later.
Bye. Thank you.
Bye. Have a good weekend. Stay inside, stay safe.
Bye, Mom.
Bye. Bye, David.
Bye.
Bye. All right.